We will proceed in the product rule of in calculus, and we will see the kind of logarithmic way to prove it. Okay, so we will see the product rule in the calculus, and we have reached to the product rule in a way. I have put light, it's too early, I believe so. So there is no natural light. Okay, so product rule where we have reached. Why product rule? So we have demonstrated that in calculus the basics of in calculus the basics of calculus is integration, and integration is nothing but the way to calculate the collection while calculating the area in algebra. So if I have a rate of collection and if I draw a graph of rate of collection, and then in that graph, means if I have rate of collection, if I draw the graph, then what is the net collection? Like if someone is collecting 3 oranges per day, then how much he has collected in 10 days. Then I have x-axis as day and y-axis is number of oranges collected per day. So function over x is 3x to the power 0. 3x to the power 0 or 3. So x-axis is x-axis and altitude is 3. So if I draw a graph of this, then graph will come parallel to the x-axis where height is 3. Okay. Now if I want to calculate the net collection, then it is area of the graph, that is width by height. If I want for 10 days, then 10 into 3, that is 30. So 30 is the area of the graph that we can see. What about if rate of collection is not horizontal rather than some other curve? Like if it is x-axis, then rate of collection is x to x square. X square. So if this is x-axis, this is x-axis, then x square is like this. If this is x-axis, then x square, this is origin, then x square is like this. If x square is like this, then how much is the area under the x square? So area under x square no one knows, but area under x to the power 0 is x. If I want height is 3 into x to the power 0, and then I want to calculate area from 0 to x, then it is 3 into x. So x to the power 0 becomes x to the power 1. This is what we have talked many times. And then if I have this being origin, if this is if this is the if this is x-axis and this is the equation, then this is x. This is a straight line, then it is x. The area under x is area under triangle. Area under triangle, we can calculate a parallelogram, and then area under triangle is width into height. That is the area of parallelogram, and this triangle would be half of it. Or, or we can consider a rectangle for which this triangle is half. If that is the case, then integration of x to the power 1 is x square by 2, because area of a rectangle is x square by 2. So if the rate of collection is x, then integration is x square by 2. So we come to an equation where x integration of x to the power n is x to the power n plus 1 divided by n plus 1. So that is the what we proceeded. This is how we proceeded in calculating the integration. Then sinusoidal. The integration of sin x is cos x, and like that, then exponential is exponential, logarithmic is 1 by x. So many things will be built upon each other. So most basic is polynomial, x to the power n plus 1 divided by n plus 1. Based upon that, we calculated the sin x. Then based upon that, we calculated the cos x, tan x, ex, log ln x, so many things. So this is how we proceed. Other way, if you know the area, then immediately you can say the integration of this algebraic equation is this. Or if you have any function gx, if fx is the function, if fx is the function for which integration is gx, Then search for any gx for which differentiation back is fx. Then gx is integration of x. This way also we calculate the integration. So one of the things that comes in y calculus, we understand that we need the net collection from the rate of collection. So we go by area way. That is y calculus. How calculus? When it comes to the picture, then we go step by step. We one step lower, then next step, next step, next step, next step, higher, higher, higher. We go with it. Now it comes as more towards it. How calculus? Not only particular algebraic equation we want the calculus, we want it's kind of little complex in a sense that if it is multiplied, consider that someone want integration of sine square x into cos x, but he knows only integration of sine x and cos x. He doesn't know sine square x into cos x. Then there is something called, then one solution to it is someone has to find that what is the solution as far as multiplication is concerned. The sine square x into cos x, okay, and then sine square x itself is sine x into sine x. If that is the case, then in case of multiplication, what is the integration? No one knows. This is called product rule in integration or integration by part. But can we try other way? If I have function fx for which integration is gx, can we try gx whose differentiation is fx back? Can we try product rule in differentiation, that is gx? So product rule in gx. So if I have a function, okay, if I have a function, consider I have a function that is ux and vx, v for victory, okay, v for viceroy, okay, v for anything you think uvwx, okay. So if I have a function ux, u is a function on x, u is a function of x, and v is a function of x. So u into v, what is the differentiation of u into v? So one way we showed that integration of u into v is nothing, u into v, it is nothing like, it looks like two sides of a rectangle whose area is u into v. So if I differentiate u into v with the x, then one delta a will come into the picture. U into v I can replace with a, and then d u into v by dx, one delta a will come into the picture. Whatever, one area will come into the picture. Okay. If I have a rectangle, whose one side is u and other side is v, then area of the rectangle is u into v. If I got duv by dx, some area, then area I can make in two parts. One is area 1, one is area 2. So if this is a rectangle, base is u and height is v, then along the v there is a strip that is added. If this is a rectangle, this is u and this is v, then here also we can consider along the v there is a strip got added. Because we did differentiation, one area comes into the picture. That strip has height of v and width as du. If it is u, then d, because we are differentiating. Same way, if I have u and v as a rectangle, then along the u, I got one area that is attached like this strip, where width is u and height is dv. If that is the case, then the whatever the area we have got along these two sides, one side area is v du plus u dv. This is area philosophy. What is traditional philosophy of the area is, if I differentiate u into v with x, okay, I'll try if light has come. Okay, so this is natural light. Okay, so the concept is that if we want now, what is the traditional way traditional way of calculating u differentiation of u into v. The traditional way of calculating the differentiation of u into the traditional way of calculating the differentiation of u into v, consider whatever it comes, then it will be differential. Du into v by dx, whatever it comes, it will be it will have share of the gradient of u and it will have share of gradient of v separately. So if I have a rectangle whose width is u and height is v, then for u consider the share is du. If it is u and it is v, then on top the share for the v. Okay, so if this is the rectangle, if it is u and it is v, then share for u is du. Du, differential gradient of u. If it is v, then share for v is dv. Then this is the strip got added and this is strip got added, and there is a corner strip that is du into dv. Now this strip has area that is u into dv, and this strip has area that is v into du. This strip has area du into dv. So du into dv we can discard as far as approximation is concerned, where du and dv tends to 0. If that is the case, then the duv by dx is nothing but u dv, this area, that is u dv, and this area plus v du. So this is also differentiation by product rule. People find out. Whatever is the case, we have proved this way, then we have proved another way, that is our way. What is our way is that let's consider this is kind of this is consider this is xy plane. This is xy plane where this is x-axis and this is y-axis. This is x-axis and this is y-axis. This surface is kept on the xy plane. If surface is kept on the xy plane, then this is going along x-axis. I'm sorry, from my side if I show, then this is going along x-axis and this is going along y-axis. If that is the case, then this surface is kept on the xy plane. If I keep y-axis constant, if I just you can say that if I just hold it, fix it, and then move this like this, okay, then how much it tilted? What is the height that it is moving? It depends upon the x. If x is 0, then it did not go up anyway. If x is this much alpha, then it went this much high. Okay, if x is this much, then it went this much high. So depending upon the x, the height, we can see how much it achieved. If it is kept on the xy plane, then there is no height at all. But if I hold it here, clinch it, hold it here, and then move like this, then at different x, the height is different. So at any x, what is the height? The height is, if it is kept on the xy plane, if this is kept, the surface is kept on the xy plane, this surface has some equation. The equation of the surface is, consider the equation, it is kept on xy plane. This is what I am saying. Okay, this is xy plane. Consider it is kept little up, and this is xy plane. What is the equation of this surfaces? So surface equation in algebra, line equation in algebra is y equal to dy by dx into x. Surface equation in algebra is z equal to dz by dx into x plus dz by dy into y. How it achieved is, if this is xy plane, and this is the surface kept somewhere, if I hold this y axis, means this side, and make it up, how much up it went from the where it was kept, that z value is nothing but dz by dx, that is the slope, dz by dx into x. If I want how much it went up, then this much. If I want how much it went up, then this much. If x is more, then height is more, that it achieved because I tilted it. So dz by dx, whatever the slope is into x is more, the height is more. Similarly, if I hold this is xy plane here. This is xy plane. If I hold this here and then move y-axis, how much it went up depends upon the y. If y is 0, then it did not go up. If y is here, then this much it go up. If y is here, then this much it go up. So y is more, then that much it went up. How much it went up? Dz by dy, that is the slope, into y. If I do together, if this is xy plane and this is like this, then first keep the y fixed and then move x. How much it went up? Dz by dx into x. Then keep x fixed and move this like this, or keep this side fixed and move like this. Okay, first it is this is xy plane and it is kept like this, kept like this. Now you keep y fixed and then move the x-axis. How much it went up depends upon distance, this x distance, that is dz by dx into x. Then look like this one, leave like this and hold the x-axis and rotate y-axis. It went even up. So see this corner. Earlier it was here, but now it is went up. How much it went up from the previous location? If this is the location, and if I fix any x comma y point, this is xy plane, and I take any point x comma y here, and then go up. If I at this point x comma y point, then what is the distance that it went up? That is dz by dx into x. Now holding the x, if I move y, then how much it went up? Then dz by dy into y, that much extra it went up. So next z that we can see that it went up is dz by dx into x plus dz by dy into y. That is the kind of algebraic equation. That is the kind of algebraic equation we for the surface, flat surface in algebra in 3D, z equal to dz by dx into x plus dz by dy into y. We are reiterating this proof because this is the most solid proof and this is what we have brought it. So it is something like it is not there, it is not available anywhere else. So if I have z equal to dz by dx x plus dz by dy y, what is gradient? So delta z equal to dz by dx delta x plus dz by dy delta y. Okay, so delta z equal to dz by dx delta x plus dz by dy delta y. Now, what is z? Consider z. Now, z is fxy, function over x comma y. Consider fxy equal to x into y. That is a function. I can take anything as far as function is concerned. So, fxy equal to x into y. So, what is gradient of fxy? Gradient of dfxy or delta fxy. Fxy equal to x into y. Fxy equal to x into y. Consider consider a function called ux. Consider a function called vx, where ux equal to x and vx equal to y. Consider like this. No one stops us. Ux equal to x and ux equal to vx, v for victory, vx equal to y. Now we want gradient of z, delta z equal to dz by dx delta x plus dz by dy delta y. So delta z is nothing but gradient of u into v, because earlier gradient of fxy equal to dfxy by dx into x plus dfxy by dy into y. Gradient of fxy equal to dfxy by dx into delta x plus dfxy by dy into delta y. If that is the case, now I replace fxy with xy because fxy equal to xy. Gradient of xy equal to dfxy by dx into delta x plus dfxy by dy delta y. If that is the situation, then we replace xy with u and v, ux and vx. So gradient of ux and vx, this is what we want. We want differential gradient of multiplication of two functions. So gradient of ux into vx. Gradient of ux into vx equal to du into v by x will be replaced by dx, x will be replaced by u. So du into v by du and delta u, delta x will be replaced by delta u, plus du into v by dv into delta v. So delta u into v by du will be considered as partial derivative along u axis. So delta u into v by delta u will be v. So v delta u plus du into v by dv will be considered as partial derivative along v axis. So it will be u into dv. So differential of u into v equal to v du plus u dv. Okay, so this is the most solid proof among every proof. Then we prove through polynomial also, that you have to watch previous, otherwise it will become long. Anyway, idea was to show the what we have done repeatedly. Now we can prove this through logarithmic also. Consider that I have to find the differential of u into v. U into v. Consider I take logarithmic of u into v, ln, natural log. So logarithmic of u into v, logarithmic of u into v equal to logarithmic of u plus logarithmic of v. That is the inherent nature of u and v. Logarithmic of u into v equal to logarithmic of u plus logarithmic of v. What is, now let's calculate the differential of both sides. Then differential of logarithmic of u into v equal to differential of logarithmic of u plus differential of logarithmic of v. Now let's go by chain rule. Let's differentiate with uv itself. Differentiation of logarithmic of uv with x we are trying. So like differentiation of logarithmic of uv with uv itself into differentiation of u into v. Differentiation of logarithmic of u into v is nothing but differentiation of logarithmic of u into v by du into v into differential of u into v. So that will become 1 by u into v into differential of u into v. This is what we want. So 1 by u into v into differential of u into v. Differential of u into v we want. Okay, that is the scenario. Then differential of u into v equal to 1 by u into v into differential of u into v equal to differential of logarithmic of u plus differential of logarithmic of v. What is differential of logarithmic of u? Let's go by chain rule and differentiate with u and then du. So ln u d ln u by du will be 1 by u. So it will become 1 by u du plus 1 by v dv. So I have 1 by uv into differential of u into v equal to 1 by u du plus 1 by v dv. Now u into v, if I push on the right hand side, then it will become v du plus u dv. So differentiation of u into v, differentiation of u into v equal to u dv plus v du. How many ways we have proved now that the product rule in differentiation. Product rule in differentiation. So product rule in differentiation is I have a function ux and vx. If I go with multiplication u into x, d u into x, that is nothing but u d vx plus v d ux. Okay, if that is the case, then let's try finding out the differentiation of sine square x into cos x. Sine square x into cos x. Consider ux is sine square x and vx is cos x. I may not get the full result, but how we will proceed? If that is the case, then first you keep u, then dv plus v du, or v u and v, u dv plus v du. So u is sine square x, so sine square x, and differentiation of cos x is minus sine x. So minus sine to the power 3x plus cos x I have to keep outside, and then differentiation of sine square x, that I don't know. Differentiation of sine square x, that I don't know. So I can go through polynomial way also. Differentiation of sine square x through chain rule will become 2 sine x cos x. 2 sine x cos x. So net differentiation is 2 sine x cos square x minus cos to the power minus sine to the power 3x, or differentiation of sine square x is nothing but sine x into sine x. Differentiation of sine x into sine x. So as per the product rule, first one sine x I have to keep outside, and then differentiation of sine x is cos x, plus one sin x I have to keep outside, then differentiation of another sin x is cos x. Sin x cos x plus sin x cos x, 2 sin x cos x. So minus sine to the power 3x plus cos x into 2 sin x cos x. So it becomes 2 sin x cos square x minus sine to the power 3x. So through chain rule also, or through product rule also, we can calculate the differentiation. What is the differentiation of x to the x square? That is x square, then it is x to the power, if it is x to the power 3 by 3. Let's go by multiplication rule. X to the square differentiation is 2 into x. Let's go with the multiplication rule. X square is nothing but x into x. So one x you keep outside, and differentiation of another x is 1. So x plus one other x you keep outside, and differentiation of x is 1. X plus x, 2x. So integration differentiation rule for the product rule is proved, that if I have two functions u into x, u into v, then differentiation is du dv plus v du. Now I said that if there are three ways we calculate the integration. One is through area. If I know the area, if I know the area of algebraic graph, quickly I can say this is the integration. Next is if I break into smaller part, and a smaller part step kind of layer by layer. If I want to calculate the different integration of an algebraic equation I don't know, then I'll break into lower level, then lower level, till I find the integration form. In that case, then we can go and calculate the integration. Third way is, if I want to calculate integration of fx, I know any function gx for which differentiation is fx, then gx is the integration of fx. Now, for any function gx, if any function gx, that is ux into vx, differentiation is, for that differentiation, I know differentiation is ux plus vx, u dv plus v du. I am not saying this is what I am trying to get the integration for. Integration, again we are trying for the multiplication only. U into v. Here we tried multiplication. How we can take help of this? Let's proceed. Okay. Now we are trying to find differentiation of u into v. U into v differentiation is u dv plus v du. Okay. What is u dv? U into differentiation of u into v equal to u dv plus v du. U dv you keep on one side and rest in other side. So u dv equal to uv minus v du. U differential of v, u dv equal to u into u dv equal to u differential of u into v minus v du, or differential of u into v. If I take this side, then differential of u into v equal to v du plus u dv. So u dv equal to d of u into v minus v du. That is v u dv. U dv equal to d of u into v minus v du. This is what we saw now. If that is the case, consider that du equal to any h. D differential of u equal to h. Differential of u equal to h. That is u equal to integration of h. If du differential of u equal to h, then u equal to integration of h. Now we have v du. V du. I'm right, right? If I had taken v du, anything I can take. Consider, I think we have taken v, u dv equal to d of u into v minus v du. U dv equal to d of u into v minus v du. Consider v equal to h, vx equal to d of vx, differential of vx equal to hx, differential of vx equal to hx, then vx equal to integration of hx. So u dv is nothing but u integration of hx. I'm sorry, u dv is nothing but u into hx, u into hx, u into hx, dv equal to hx, v equal to integration of hx, h. So u into dv is u, h, u into h equal to differentiation of u into v, differentiation of u into v, u into v is integration of hx minus v into du, v is integration of h and then into du. Let's do integration of whole stuff. Okay, I'll reiterate. We tried u dv equal to d of u into v minus v du. Let's do integration everywhere. So it becomes integration of v, integration of d into d, integration of u dv. We do integration everywhere. Our side is u dv equal to du into v minus v du. Let's do integration everywhere. So it becomes integration of u dv equal to d of u into v. D will go away if I do integration. So u into v. U into v. If I do integration, it becomes u into v. So integration of u dv equal to u into v minus integration of v du. Now dv equal to h. So v equal to integration of h. Now we have integration of u dv. So dv is h. Now integration of u and h. This is what we want. Through integration by part, what is integration of two multiplication? So u into hx, integration of u into hx, this is what we want, equal to u into v. So v is integration of hx. So u into integration of hx minus integration of v du. Integration of v du. V is integration of hx. So integration of u into hx to function u into hx equal to u into integration of hx minus big integration of hx and differentiation of u. So this is integration by part, that integration of product that we got through differentiation only. So integration of u into h equal to then u into integration of h minus then big integration of h into differentiation of u, or integration of two function fx and gx, integration of two function fx into gx equal to f integration of gx minus then in big integration of gx and then differentiation of fx. Okay, So that is integration by part or integration by part or product rule in integration. Let's calculate the integration of sine square x cos x. Integration of sine square x cos x. So first function is sine square x and second function is cos x. So if I go by product rule, then first sin x I'll keep outside integration of cos x, that is sin x. So sine to the power 3x minus and then integration of sine square x, sorry, differentiation of sine square x and integration of cos x. Okay, okay, this is how it is. If I have done something wrong, then this is how it is. Okay, so I'll do it again. So the u dv, u dv equal to du into v minus v du. If I take v equal to v dv equal to h, and then we do full integration u into dv, full integration, we are trying to calculate integration of u into h because dv equal to h, u into h. If that is the case, then integration of d into d of u into v is nothing but integration, it is nothing but simple u into v. Then it becomes u into integration of hx, u into integration of hx minus big integration v du. V is integration of hx and then du. Okay, same thing. Now we have du. So whatever u is remaining, u I have taken as first function. For that I have to calculate differentiation, and second function I have taken, that is hx. For that we have to do integration here also and integration there also. Now I have sine square x cos x, sine square x cos x, for which I have to calculate the integration. So first consider ux is sine square x and hx is the cos x. So ux and integration of hx. So sine square x, again sine x, sine to the power 3x minus big integration and then big integration and then integration of the whatever integration we had calculated cos x. For that only we have to calculate the integration again. So integration of cos x and differentiation of sine square x. Okay, okay, this is how it is. So or differentiation of sine square x and integration of cos x, whatever. So the integration of cos x is again sin x, and differentiation of cos square x, cos differentiation of sin x. I am doing some really rubbish. I have to calculate integration of sin square x into cos x. That will be sin square x integration of cos x. So sin to the power 3x minus then differentiation of sin square x integration of cos x, or integration of cos x in differentiation of sin square x. So differentiation of sin square x is 2 sin x cos x, and integration of cos x is sin x. So then integration, then it will become 2 sin square x cos x integration minus. So this whole step I can take it. I am trying to find integration of sin square x, that is nothing but equal to sin to the power 3x minus integration of 2 sin square x cos x again. So if I take this left side, it will become 3 sin square x cos x dx equal to sin to the power 3x. So 3 I can take this side, then it is sin to the power 3x by 3. Oh, okay. So we will end this chapter, we'll close this chapter as product rule, to find product rule in integration. The product rule in integration, how we can find is, we found the product rule in differentiation through so many ways, and we rearrange that, that is product, that is u differentiation of uv is nothing but u dv plus v du. u dv, u dv I kept one side and other on other side. U dv equal to differentiation of u into v minus v d. We consider v as h, dv as h, then v equal to integration of h. If I replace everywhere, then integration of u into h equal to u into integration of h minus minus big integration of h and d. So this is integration by part or product rule. Can you see how we are proceeding? We started with polynomial and then we proved for sin x we took a circle and trigonometric way we proved the integration of sin x is minus cos x. If I know integration of sin x is minus cos x, okay, integration of sin x is minus cos x, then we came to know that integration of cos x is sin x, because sin x is nothing but a square root of 1 minus cos square x. Okay, that way we proceeded and we calculated till tangent. Okay, and then now product rule. This is the way how the calculus grow in a tree in this fashion. So this is how it is. And and kind of, if more things comes into the picture, then we will talk about it.